So there are a couple problems inherent with working with angles in the unit circle. For example, if I want to evaluate the angle pi over 6 or the sine of pi over 6, no problem. I already know that the sine of pi over 6 equals 1/2 and I'm done. But what happens if I want to look not at pi over 6, but I want to look at 13 pi over 6? So the sine of 13 pi over 6 equals 1/2. But how would I know which angle I'm dealing with? They're coincident angles, they're coterminal, they end up in the exact same place, but they're distinctively different angles. In fact, I could even go further and say, well, what is the sine of negative 11 pi over 6? Negative 11 pi over 6 also equals 1/2. These are three distinctly different angles, same trig function, easy enough to hold in my head, but visually on the unit circle, I can't really do very much with that. So we're going to graph on a Cartesian plane. So the Cartesian plane is a bit elongated, and you'll see why in a minute. We're going to graph the common angles in turn to see what happens if I transport them onto the Cartesian graph. So let's start at the beginning where theta, the angle theta, equals 0. Now we can't put all of the functions, sine, cosine, and trig, you'll see why in a minute, on this, but I can say that my horizontal axis will be theta, or my angle, and then the vertical axis will represent the values of the sine of theta. So first, if theta equals 0, what is the sine of theta? Well, sine is y, and y at the angle theta equals 0 is 0. So next, let's look at the sine of 30 degrees. We're only going to do the common angles here. So 30 degrees intersects here. If I mark a position on my horizontal axis for theta and say I'm now talking about pi over 6, which is 30 degrees, how high or what is the value of the sine of theta? Well, the y-axis, the value on this one, has to be exactly the same as the value on this one, which is 1/2, and I can plot that point. Moving on to 45 degrees. Again, the sine of 45 degrees on the unit circle will have to have the same value. Well, let's actually put 45 degrees on my graph, and I can tell that these are going to space out funny, so let's go ahead and space these. If I say this is pi over 6, pi over 4, 45 degrees, pi over 3, 60 degrees, and then pi over 2 for 90 degrees, then that would be pi. And the same distance would be 3 pi over 2, or 270. And then the same distance would be 2 pi, and at that point I've gone all the way around the circle. Okay, so let's put in our pi over 4 now. Pi over 4 is the same elevation, or the value of root 2 over 2, and that would fall right here. And then pi over 6 would be slightly higher at root 3 over 2. And then pi over 2, well, we know the sine of 90 is all y, and on the unit circle, the radius equals 1, so pi over 2 would be right here at 1. So what happens on the other side then? Well, the first angle I'm going to encounter is going to be 2 pi over 3, or 120 degrees. The next angle is going to be 3 pi over 4, or 45 degrees. And then the next angle, or the last angle in the first half, or the upper half of my plane, is going to be 5 pi over 6. Or 150 degrees, and then I'll encounter pi on the other side. So let's see what happens using the same evaluation to the to the elevation or to the outputs. So 60, or excuse me, 60 times 2, so 60 degrees plus another 60 degrees, is going to take me to the exact same value of y I was at before. So straight across right here, I'm going to end up in exactly the same place. For 45, reference angle 45 in the second quadrant, I'll end up again at the exact same elevation as 45 in the first quadrant. Keep working. And then when I reach pi, y, my output for y, goes right back to 0. So you can see I sort of have a curve that goes up and back down. Let me kind of space these a little better. 1/2 went to 1, 2/3 went to there. All right, so that looks better. So I have a curve that starts at 0, goes up to its highest level of 1, comes back down to 0. Let's see what happens on the other side. But first, let's go ahead and put our units in. So if this is 3 pi over 2, halfway would be a 45-degree angle. So something pi over 4, there'd be 5 pi over 4. And then to the just before that would be some version of pi over 6. And that would be 7 pi over 6. And then on the other side is going to be a version of pi over 3. 3 on top plus 1 more is 4. Let's move these up above. I think they're going to get in the way. You'll see in a minute why. All right, and then we'll do the other side. So pi over 4 in the fourth quadrant. Pi over 4, how many are there? There are 4, 5, 6, 7 of them. And then in the fourth quadrant, my pi over 3, there were 3, 4, 5 of them. And last but not least, pi over 6, there were 6, 7, 8, 9, 10, 11 of them. All right, so I'm going to put the angles in, the arrows in, and then we'll come back and put the points in. All right, so I put in the angles, and I also put in the values I'm going to need. For 7 pi over 6, my elevation is going to be 1/2. For 5 pi over 4, my elevation, negative 1/2, will be negative root 2 over 2. For 4 pi over 3, my elevation will be negative root 3 over 2. And then for negative 270, or negative 3 pi over 2, my radius will be negative 1. And so then the whole thing turns right back around and duplicates on the other side, just like we did at the top. And so the curve for a sine function, not so easy to do with my pen, but let's see if I can pull it off. Maybe hit this one again. Looks like this. So I have now been able to distinguish the difference easily, the difference between sine of pi over 6 and sine of 13 pi over 6. Oh, I haven't done 13 pi over 6 yet. I would have to keep going, right? So if I have 12 pi over 6, the very next angle would be 13 pi over 6, which would have the same elevation here. So this is the difference between 13 pi over 6 and pi over 6. I have the first time around shows up on the graph here. The second time around shows up on the graph here. They have the same output value, but they're distinctly different angles. And that shows when I move my graph onto a Cartesian plane instead of continuing to work on the unit circle. That's the whole point of working with graphs on the Cartesian plane. You can see they go up. In a standard position, a sine function starts at 0, curves up through 1, curves back down to 0, curves down through -1, and then back up to 0, and then it repeats over and over and over. This is called sinusoidal. It's a sinusoidal or a periodic. If I were to graph the cosine function, and I'll do that in a different color, and I won't do it point by point, but I will evaluate it and explain what I'm doing. So at 0, the cosine equals 1, because the angle, the radius of the circle, is 1. At pi over 4, at 45 degrees, the cos function is equal to the sine function, so I get the exact same value. And then at 90 degrees, the cosine function is equal to 0. And on the other side, the same thing happens, except in the negative region, and cosine equals -1 when the angle equals pi. So at pi, I'm looking at -1. And then I swing right back up through. At 3 pi over 2, the cosine function equals 0. And at pi over 4, or excuse me, 5 pi over 4, sine and cosine have the same value. And up above, when we come all the way back around to 2 pi, cosine will have the same value as at 0. And so the cos function does the same kind of sinusoidal curve, except, oops, I didn't put in that value, except it's shifted over pi over 2 units. So if I were to pick up cosine and move it over pi over 2 units, it would lay right on top of the sine function. And both of them are considered sinusoidal because they move up and down and up and down, and periodic because once I've completed one cycle, the same thing is going to happen again and again, happen in the opposite direction as well. If I went backward and completed a cycle, the same thing would happen again and again, all the way throughout the entirety from negative to positive infinity. So hopefully it seems pretty clear to you at this stage of the game that being able to graph trig functions where each angle is represented in a different or on an axis of its own, that we can see the fact that trig graphs are periodic. They go around to the beginning, and then they go around to the beginning again, and then they go around to the beginning again, or backward, periodic, they go backward, that even though they keep doing that, and we can imagine it looking at the unit circle, it's so much easier to be able to graph it to see what did happen, or where is that 17th coterminal expression or angle for pi over 6.